Okay, before discussing the use we'll make of the triangle inequality, let's point out some consequences of this inequality that will come in handy from time to time. First of all, um, if the triangle inequality is true, then we can proceed inductively to conclude that if we add, say, three numbers and we take the absolute value, then that's less than or equal to the absolute value of A plus the absolute value of B and the absolute value of C. Proof. We're slowly getting to the habit of proving things. So we know that the triangle inequality is true for any two numbers, and A plus B is a number. So we know that A plus B plus C must be less than or equal to the absolute value of A plus B plus the absolute value of C. In turn, now we have the classical triangle inequality here. This thing here is smaller than or equal to this thing here, and we're just adding C on both sides. So in the end we conclude that the absolute value of A plus B plus C is less than or equal to the absolute value of A plus the absolute value of B plus the absolute value of C. In fact, more generally, if we have n numbers so if we have the sum from I equals 1 to n of the numbers a sub I, and we take the absolute value, that will be less than or equal to the sum of the absolute values. And the proof here is by induction. And induction is something we'll discuss in a little while, so this is should be an exercise for you once we discuss induction. It's not a difficult one, but it's a good way of getting used to proving things. Another thing is the fact that if two numbers are close, then their absolute values are close as well. So the absolute value of the difference of the absolute values of A and B is smaller than or equal to the absolute value of A minus B. So if A and B, this should be interpreted as saying that if A and B are close, then the absolute values are close as well. And proof of this, I mean, this is an exercise in the book, but we'll do it here for your benefit. So how do we prove this statement? Okay, we know by the triangle inequality, well, this is A minus B is a number, so I'm going to write it like this. So this is equal to A, right? and this must be less than or equal to the absolute value of a minus b plus the absolute value of b. And this again, the left hand side is just the absolute value of a. And so this implies that if we move b to the other side, the absolute value of b to the other side, that the absolute value of a minus the absolute value of b is less than or equal to the absolute value of a minus b. And this is all we need, actually, because without loss of generality, we may assume the absolute value of a is greater than or equal to the absolute value of b. If this is not the case, just do the same thing, but instead of writing a minus b plus b, you can write and we will want to keep it so b minus a plus a, and do the same computation. And keep in mind that the absolute value of a minus b is equal to the absolute value of a minus b is the same as the absolute value of b minus a. Okay, so we can always assume that. I mean, one of the two must be bigger than or greater than or equal than the other one, and you perform this computation above with that one. And if we do so if we assume that, then since that is positive, and if you go back to the definition of the absolute value function, then that is exactly the same as the absolute value of the difference, and then you have this inequality. Okay. So that's a very important property also. And in general, when we say without loss of generality, it means that we usually have a sort of a symmetric situation, like in this case. So a here and b can be interchanged, because this absolute value is what I was saying here is the same as the absolute value of b minus a. And this comes from the first property. That a minus b is equal to the absolute value of a minus b is the same thing as the absolute value of a minus b times the absolute value of minus 1, which is 1. And this is equal to, and we can bring the minus 1 inside, minus 1 times a minus b, all of that in absolute value, which is just the absolute value of b minus a. Okay, so this follows simply from the first property. And so when you change the roles of b and a, you get the same thing. So that's why we say that without loss of generality, we may assume that a, has an absolute value that is greater than or equal to b. If not, well, you do the same thing for b instead of a. Okay, so these are the very important properties. Now, another very important thing to keep in mind is that this is the way we're going to use it, and this is something they stopped to ponder on in the book, which is the fact that, let me see how we things. Yeah. So we have the 2, then we didn't number the properties. The thing is that a minus b is less than or equal to a minus c plus c minus b. So it turns out that sometimes when you want to prove that two things are close, like a quantity a and b, you know that a is close to c by using some hypothesis or some assumption, and you also know that b is close to c separately. And so if you know that these two quantities on the right hand side are small, then you can conclude that a and b are actually close to each other as well. And how do we prove this? I mean, again, the proof just follows from the triangle inequality. We have two numbers, a minus, so you have a minus b, right, in absolute value. This is the same as the absolute value of a minus c minus b minus c. So here the c's cancel out, so you get a minus b. So you have two numbers here, and this is the same thing as the absolute value of a minus c plus c minus b, if you want. And we have two numbers, a minus c and c minus b, and we apply the triangle inequality to those two. So the absolute value of a minus c plus the absolute value of c minus b. This is less than or equal to that. I'm sorry. Sorry about my writing. Okay. And now just notice that, as we showed before, we can write this as a minus c, the absolute value of a minus c plus the absolute value of b minus c. So this is actually equal to that. It's less than or equal as well. Okay, so this is just in case you recognize this formula for, this application of the triangle inequality from some other application. But this is just a basic fact that follows immediately from the triangle inequality. And remember, you can swap the order here inside the absolute values. You can consider a minus c or c minus a, because the absolute value is indifferent to such things. Okay, and finally, to conclude, what's important? To present a little bit of what's important about the triangle inequality and about the absolute value function. And the way we're going to conclude this, some things are equal to 0 or small. Usually this will happen after taking limits. But this is what it's presented in the book as theorem 1.2.6. Two real numbers, a and b, are equal if and only if, maybe you're not familiar with that notation, if and only if for every epsilon greater than 0, it follows that a minus b is less than epsilon. So what is it saying? That if you find that the absolute value of a minus b is smaller than any positive number, then in fact that absolute value is equal to 0. Okay, and again, well, the proof here will highlight two things. One is that whenever you are given a proposition that says if and only if, you need to prove two things, which is how we'll split the proof here below. And the other thing is to give yet another example of proof by contradiction. Okay, so the first thing is if you have a if and only if, you need to prove that if you start proving P is equivalent to Q, so P if, which is the same thing as P if and only if Q is the same, saying two things hold at the same time, which is P implies Q and Q implies P. So we need to prove two things. So the first thing we'll do is we'll assume here that two real numbers are equal, and then a and b are equal. So this is implication. So we start from a being equal to b, and then we'll show that for every epsilon, the absolute value of a minus b is less than epsilon. So if a is equal to b, then we know that the absolute value of the difference is the absolute value of 0, which is just 0 by definition. And this is smaller than epsilon for every epsilon greater than 0, right? And that concludes the proof of that implication. Now, starting now from the fact that for every epsilon, the absolute value of a minus b, for any positive epsilon, the absolute value of a minus b is less than epsilon, we have to conclude that a and b are equal. Okay, so this corresponds to the other implication. We proceed by contradiction. We assume that a is not equal to b. Then a minus b will be some number. I mean, the absolute value of a minus b will be some number, which is the distance between the two, which is greater than 0. Okay? And then what happens? But we know, I mean, the thing is we'll get a contradiction because we know on the other hand that a minus b is less than epsilon for every epsilon greater than 0. So in particular, we must have at the same time that a minus b is less than r over 2. So this is a particular choice of epsilon. Remember that we're allowed to choose any positive epsilon, in particular r over 2. But we also have that the distance between a and b is equal to r. And that's a positive number. So the only way these two things can be true, so this will imply that r would have to be less than r over 2. Moving on to the other side, we get that r would have to be less than 0, which is a contradiction. This is how we write a contradiction. Okay, so this cannot be true, so that means that in fact a and b are equal.